We've looked at different methods or ways by which heat can be transferred. We've talked about conduction, convection, and radiation. Now, for conduction, we know that this takes place in solid. Convection, this takes place in fluid, and radiation, this does not require any material medium. Now, let's look at the ways of preventing heat loss. One way of preventing heat loss is when we use a vacuum flask. Let me explain this. If you peradventure you have a liquid and it's very hot and you don't want the heat energy to be lost, or you have a liquid that is very cold and you want to keep the coldness of that liquid, you are going to use a thermal flask, which is also known as DEWA or vacuum flask. Now let's look at the working principle. Now, your vacuum flask consists of a cap, a cork stopper, a vacuum. Then you have your liquid inside it, hot or cold. You have a swivel surface. You have double wall metal or plastic container. Then you have a insulated support. Now, what we are using this vacuum flask to do is we are using it to prevent heat loss or heat gain by our liquid. So you are preserving your liquid, you are preserving the heat of your liquid. So let's look at the first one is using the silver surface. You know that a silver surface is not going to absorb any radiant energy that falls to it. So if you shine a light into a silver surface, that light will automatically reflect. 100% of that light will be reflected. Unlike a black body that if you shine light, any radiant energy that falls on a black body is going to absorb everything compared to silver surface. So silver surface definitely is used to prevent heat loss by radiation. Now let's look at the vacuum. Vacuum is just like a space. Now vacuum is used to prevent heat loss by convection and conduction. Now let me explain this. Now we have a vacuum here in between the container that will contain your liquid and the outer part of your flask. Now this is a space here called vacuum. You see that vacuum? So it's used to prevent what? Heat loss by convection and conduction. Now let's look at insulated support or cork support. Now this insulated support or cork support is used to prevent heat loss by conduction. Now this one is used to prevent heat loss by conduction. Then let's look at cork stopper. Cork stopper prevents heat loss by evaporation. Sorry about this. By evaporation and convection of the liquid. This is the cork stopper and it prevents heat loss by evaporation and convection. Now you discover that even though you are using this device to prevent heat loss or heat gain by your liquid, you discover that after a while your liquid is still going to lose heat. The heat will still be lost. If you pour there, I don't think there is a flask that will prevent heat loss in a fluid. Let's say you have a hot water and you put it inside flask, and that flask is going to prevent the heat being lost for a very long time. Let's say for 2 weeks. It's not possible. So that means heat energy will still be lost. Heat will still be lost. So let's look at the process by which heat can be lost even though you are using a vacuum flask. The process is this guy that is here. I used to see question here. Now this guy that is here. Now, due to the conduction, don't forget that let's say we have hot water here, then vapor will rise here, and due to convection, this cork stopper will still be absorbing some energy. Due to what? Due to conduction, it's still going to be conducting energy. That means the cover of your flask, that plastic cover of your flask, will still be absorbing some heat energy. Then from that, heat will be lost. After a while, you discover that your water will not be cold as it is initially again. The same thing with will be hot as it is initially again. The same thing with cold water as well. So which means that the heat is lost by this what due to this cork stopper. So which means after some days or few hours, this thing will start conducting it away. So that is one of the way of by which heat is being lost in your vacuum flask. All right, let's proceed. Now we've talked about the various effects of heat, and one of it is what change of state. Now change of state or change of phase. Now the first thing we are going to talk about is boiling, and boiling is this is the spontaneous changes of liquid to vapor when the temperature of the liquid is raised to its boiling point. At the boiling point, the vapor pressure of the liquid equals the atmospheric pressure or the external pressure exerted on the liquid, causing bubbles of vapor to form within the liquid. These bubbles rise to the surface and it escapes into the air. Now, boiling takes place at a certain temperature, at a constant temperature. Now, when we have spontaneous emission, also spontaneous change of liquid to vapor at a constant temperature, that is what we call boiling, because normally liquid can change to vapor at a temperature that is even below the normal boiling point. So which means that evaporation is different from boiling. Now let's look at difference between evaporation and boiling. The first thing we are going to look at is the boiling versus evaporation. You see, boiling is a spontaneous or rapid change of liquid to gas or vapor at constant temperature boiling point due to heat, while evaporation is the change of liquid to gas. Now the change of liquid to gas or vapor is known as evaporation, while boiling is spontaneous or rapid change of liquid to gas. Now evaporation is happening rapidly and not just at any temperature, at a constant temperature. But for evaporation is the change of liquid to gas. So which means boiling, as boiling is taking place, evaporation is also taking place. Unlike evaporation, that the liquid is just changing to vapor at any temperature. Now let's look at the second one. Boiling takes place throughout the entire volume of liquid, which means boiling is taking place throughout the entire volume of your liquid. Unlike evaporation that takes place at the surface. Oh yeah, look at this. Evaporation takes place at the surface. The next one, wind can affect the rate of evaporation, and wind has no effect on boiling. That's the difference between boiling and evaporation. This type of question used to come out in WAEC. Now let's look at it. So we are still talking about evaporation and boiling. So we've talked about all this. So effect of pressure impurities on boiling point and melting point. Now the first effect, we are looking at what will happen if you are increasing pressure or reducing pressure, or you are adding impurities to a liquid. What will happen to the boiling point? Now boiling point increases with increase in pressure. So which means that if you increase pressure, the boiling point of a liquid will increase. Increasing pressure will increase the boiling point, which means that for instance, if you increase the pressure, you want to boil water and you increase the pressure, automatically water is not going to boil at the normal standard pressure, which means it's not going to boil at the temperature that we all know, which is what, 100 degrees Celsius. That's the atmospheric pressure. Now increasing the pressure will definitely increase the boiling point. Instead of boiling at 100 degrees Celsius, it's going to boil at an higher temperature compared to the normal boiling point. Now the next one is, which means if you reduce the pressure as well, you have the boiling point will reduce. Now let me explain this. Pressure cooker is a practical application of effect of pressure on boiling. Let's look at atmospheric pressure, for instance. You see that as you are moving up, as altitude is being increased, the atmospheric pressure starts coming down. So as you are increasing in altitude, as you are going up, the pressure, the atmospheric pressure, the atmospheric pressure exerted on any object will start reducing as you are moving upward. So which means that if you are boiling water at the normal sea level, and you now climb a mountain, a very high mountain, and you want to boil water there, now the water will quickly boil if you are boiling it on the mountain compared to when you are boiling it on the normal level. If you are boiling it on the normal level, we have normal pressure, normal atmospheric pressure. But as you are ascending, the atmospheric pressure starts dropping. So which means that the pressure is being lowered, and automatically the boiling point will reduce. Now, one of the application of effect of pressure is pressure cooker. Now, if you want your food, let's say you want to cook yam, for instance, you want to cook yam and you want it to quickly, you want the yam to be prepared quickly, you want it to easily cook. Now you discover that most time there is something we used to do and we don't even know that it's actually physics. Now you cover it with a nylon, you now cover it with a pot. What we are actually doing is we are trying to increase the pressure. Another example is when you want to cook something, I think, is it not all this what's it called, biscuit, that they used to do like that? They will cover it and then they will try to put the cover and put a big stone on the pot. What they are trying to do is they are increasing the pressure, and automatically as you're increasing the pressure, the boiling point of that thing that you're cooking will increase. And as you're increasing the boiling point, it means that it will take in more energy for that thing to boil. And as it is taking in more energy, so your food will easily cook compared to if the boiling point is not raised. That is the application of pressure cooker. Now, pressure cooker is going to increase the pressure and automatically increase the boiling point. So which means that more energy will be absorbed before that thing starts boiling. As more energy is being absorbed, that means whatever you are cooking will easily cook. You won't waste more time while cooking. Now let's look at it. Melting point increases with increase in pressure for pure substance, but it decreases for ice. Now if you are increasing the pressure, automatically the melting point of any pure substance will start increasing as well. But you know, water is something that is very special. It has some kind of property that are not normal. Anomalous behavior of water. This is another example of anomalous behavior of water. Now, for instance, for pure substance, but it decreases for ice. Now, melting point increases with increase in pressure for pure substance, but it decreases with there's a practical application or demonstration of decrease of decrease in the melting point of an ice if you are increasing pressure. It's called regulation. That term is known as regulation when you put a string and you put two different weights at the end of the string, and you have an ice and you try to suspend those two mass on the ice with that string. You discover that the string will pass through the ice successfully without cutting the ice, which means the pressure is increased and the melting point is lowered, and your string will successfully pass through the ice block. Ice. Let's look at pressure cooker. Now we've seen how pressure affect the boiling point of liquid. Now, as you are increasing the pressure, automatically the boiling point starts increasing. the same thing, let me explain this for you guys, because you can see question coming out on this. Now you discover that if you are doing mountain hiking or you are climbing up a mountain, your altitude is increasing, and as a result of increase in altitude, the atmospheric pressure starts coming down. So the normal atmospheric pressure we used to use while solving our chemistry question, physics question at atmospheric pressure 1 atmosphere means that we are at the sea level. Now anything above the sea level, which means you are ascending, ascension will result to what? Reduction in atmospheric pressure. Now as you are reducing the atmosphere, which means that if you are climbing up a mountain, you are on a mountain, let's say for instance, let's just imagine we have someone that is at the top of the Mount Everest. Now it's boiling water. Now if that person is dipping his thermometer inside that water, he will discover that water will start boiling at a temperature below 100 degrees Celsius. Now because the pressure has reduced, the atmospheric pressure has reduced, that is why most time you waste a lot of energy while cooking on the mountain, because of the fact that you have reduced the boiling point. As a result of that, the water will start boiling at a temperature that is below its normal temperature, which means you take less heat to boil wherever you are cooking. And as a result of less heat, what we actually need in cooking our food is the heat, not the temperature. It is the heat. Now as a result of reduction in the heat while your food will boil, it will result to what? Longer time in cooking your food. So if let's say you are cooking rice, normally you are cooking rice for 30 minutes. Now if you climb up a mountain and you want to cook rice with the same amount of heat, let's say with the same device, let's say for instance you have a gas cooker and you carry it up a mountain, you want to use it to cook your food, instead of spending 30 minutes, you will end up spending like close to 1 hour or above 45 minutes, due to the fact that the boiling point has reduced. Now that is why it is very important for mountain climber to have this device known as what? Pressure cooker. Now what we use pressure cooker to do is we use it to increase the pressure inside your pot. We have pressure pot or pressure cooker. Now we use it to increase the pressure inside the pot. Now let's look at it. We have a pressure regulator here. We have overpressure plug, sealing ring, the cooling rack here. Then we have the handle, we have the body, we have the air vent and vent pipe. All these things have their functions. Now the pressure regulator will regulate the amount of internal pressure you want to apply in whatever you are cooking in this pressure pot. Now what pressure pot is actually doing is that it is increasing the pressure. As a result of that, anything that you are cooking inside this pressure pot will not boil at the normal temperature it's supposed to boil, because you have increased the internal pressure, which will result to what? Increase in the boiling point. As a result of that, for that thing to boil, it will take in a lot of energy. Now, as a result of that, your food will take less time to cook, to be done. So if you are using pressure cooker, you discover that you are using it to cook rice. Within few minutes, your rice is ready. That is the function of pressure cooker. That is why mountain climber will always carry this kind of cooker along, because they know that they will spend a lot of time in cooking up the mountain. Another thing you need to know is the variation of pressure, atmospheric pressure with altitude. As the altitude is increasing, the atmospheric pressure starts coming down. The atmospheric pressure starts what? Coming down. That is why above the sea level we have 1 atmosphere, which is correspond to what? 760 mmHg. Now if you want to dive into the sea, you are in the sea and you want to dive inside the sea, you discover that you can only get to a certain point, because as you are diving in downward, you are increasing the depth. As you are going low below the sea level, the pressure will start increasing above the sea level, pressure reduce, below the sea level, pressure starts increasing. So as you are diving in, you discover that we get to a point you can no longer dive deep again unless you need any machine or any device that will help you, that will support you due to intense pressure. So as the depth is increasing, pressure is increasing, and we can see that from this hydrostatic pressure. Pressure is equal to what? H rho G. We have that. So any question can come in that place. We can also verify this if you have your tank. Let's say you have a tank that is full of water and you try to punch it at different level. You discover that the one that is at the base, low, you discover that the length at which the water will start flowing will be longer compared to the one that is at the top due to increase in pressure with depth. Now let's forge ahead. We have a device that we use to measure it. Don't forget that we are talking about it. I just digress a bit to explain some of the principles in physics for you guys. Now let's look at bomb calorimeter. Now bomb calorimeter is very useful in calorimetry. Now calorimetry is a process or method in which we are using to calculate different kind of heat. Calorimetry is very useful in chemistry and in physics. There's one aspect of physics and chemistry that deals with that. Now we have a device that is very useful for us, which is known as what? Bomb calorimeter. Now we have different type of calorimeter. This one is bomb calorimeter. Basically, this one is used to measure the specific heat capacity of any material. To measure what? Specific heat capacity of any material. Nobody will ask you in JAMB, but for knowledge sake, let me quickly explain some parameters we have here. So normally you have your ignition coil here, you have your bucket here, you have the air space. Basically we use air space to prevent heat loss to the surroundings. The same thing with what? Insulating jacket. You have your sample here inside this crucible. Then you have your steel bomb here. It's just like a melter. You have your ignition wire here that you can connect. Then you have your oxygen supply. You have your thermometer, you have your magnifying glass. This magnifying glass is used to look at the condition of whatsoever thing you are doing here, just to measure your, your thermometer, the temperature, just to measure the temperature. Now my magnifying glass will be connected with this guy so that you will be able to see the reading on your thermometer. So we use it to measure heat, different kind of heat, specific heat capacity. Now, heat capacity and heat associated with change of state. Let me explain the meaning of heat capacity. Heat capacity is also known as what? Thermal capacity. Thermal capacity is the amount of heat that is required to raise the temperature of a body by 1 Kelvin or 1 degree Celsius. It is measured in joule per Kelvin, and which means that thermal capacity is the amount of heat that is required to raise the temperature. Let me explain this now. Which means if you have a wood, the thermal capacity of a wood is the amount of heat that you are going to supply to the wood that will make the initial temperature of that wood increase by 1 degree Celsius or 1 degree Celsius or 1 Kelvin. Let's say you just pick a wood randomly, you pick it, let's say you just pick any wood of your choice, and that, let's just take for instance you are picking it and the temperature of the wood, initial temperature of the wood, let's say is around the room temperature. Let's have it like 32 or 34 degrees Celsius. You have it, let's have it as 32 degrees Celsius. You now pick that wood, you start supplying it to the wood. Now, heat capacity in that sense means the amount of heat that you are going to supply to that wood that will make that wood temperature to increase from 32 to 33 degrees Celsius. Or let's just say you pick that wood and the initial temperature at which you pick that wood is, let's say for instance it is 0, let's just say it is 0 Kelvin, and you are picking it, you start supplying it to it, and you want to increase the temperature from 0 to 1 Kelvin. Now the amount of heat that you are going to supply is known as what? The thermal or heat capacity. That is why it is measured in what? Joule per Kelvin. because you are not taking any measurement of the mass. What you are concerned is you want to increase the temperature. Now let's talk about the specific heat capacity. Now this one, you are specific here. You are picking a known mass. So which means that specific heat capacity is the amount of heat that is required to raise or increase the temperature of a unit mass by 1 Kelvin or 1 degree Celsius. A unit mass. Whenever you hear the word unit, means 1. Unit mass will now be 1 kilogram. So which means specific heat capacity will now be, okay, you are picking 1 kilogram of wood and you want to, the amount of heat that you are going to supply to 1 kilogram of wood to change its temperature from 32 degrees Celsius to 33 degrees Celsius. That is specific heat capacity. That is why the unit will now be what? Joule per kilogram per Kelvin, or joule per Kelvin per kilogram. Anyone you choose. That is specific heat capacity. Now, all these things that I'm talking about, they are properties of a material. It differs from material to material. Let's take for instance the amount of heat that you are going to supply to a clay pot to change the temperature will be more compared to the amount of heat you are going to supply to a stainless. Let me explain this. You discover that most of our frying pan, 90% of our frying pan, except you are from Chinese or Korean, that they usually use clay to make some of their frying pan. Now, here in Nigeria, you discover that they are using stainless. Why are they using stainless? Why are they not using a clay pot to make frying pan? It's very simple. Now, if you are using clay pot will start absorbing heat before the temperature starts increasing. That is why most time they have high heat conductivity, high thermal conductivity. So when they have that ability to start absorbing it, the more before their temperature starts changing. So that is why they are not good for making frying pan, because if you are using oil, you don't want your oil to waste. You quickly want your whatever thing you are preparing, you want it to quickly fry. That is why we are now using stainless that is having what? Low heat capacity compared to clay that is having high heat capacity, which means that if they are having high heat capacity, the amount of heat that you are going to supply to them will be so much before you start increasing their temperature compared to the other guy, stainless. So they can ask you any question as regards stainless, copper, and the likes. That which of the following is having high thermal capacity? You are expected to know all this. Now the next one is latent heat. Now whenever you hear the word latent heat is a form of heat that is associated with phase change or the state of matter, the change of state of matter. Absorbed or given off at constant temperature when a substance changes from one state to other states. Now let's look at it. It's very simple. Now this type of heat is absorbed or given off at constant temperature, which means temperature is not changing and the state of the matter of that substance will change. Now it's very simple. Now even though heat is being absorbed or given off, the temperature of that substance is not changing. Now because the heat that is absorbed or given off, now the heat that is being absorbed will be used to break down the bonding, the atomic bond that is making that. Let's say for instance we have solid to liquid. So the bond between the structure, the lattice structure of that solid will be broken in order to have what? To have a loose structure. That is what we call liquid. The same thing with liquid to gas as well. So the heat that is being supplied, that is being absorbed, will be used to break the bond between the liquid molecules so that some molecule will escape as gas. That is latent heat of fusion and evaporation and vaporization. The next one is latent heat of fusion, is the heat absorbed at constant temperature when a solid changes to liquid, while latent heat of vaporization is the heat absorbed at constant temperature when a liquid changes to vapor. Very simple heat energy formula. Now heat energy formula is, the first one here is MC change in theta. Your M is the mass, your C is a property of that material that you're supplying heat with it, which is known as what? Specific heat capacity. The T2, the next one is MC. Now this MC, we've talked about it the other time, is known as what? Heat capacity or thermal capacity. When MC together with the mass, because we are not considering the mass, that is when we have what? Heat or thermal capacity. But if we are talking about C alone, C alone means what? Specific heat capacity. That is that about heat energy. Now the next one is latent heat of fusion. The latent heat of fusion, heat that is absorbed at constant temperature, now is what? MLF. LF is used to describe the property of that material at constant temperature when the material is changing from solid to liquid. That is when we have fusion. MLF, you see, it's not having change in temperature there. The same thing is what? Latent heat of vaporization, MLF, LV. That is the formula that you can use to write the heat energy if you are supplying heat energy to anything. Now next one is heat energy transformation formula. You need to be very careful. This is very useful for you to solve some question in physics, both your WAEC and JAMB. Now the first one is electrical energy to heat energy. When electrical energy is being changed to heat energy, you should know that electrical energy, the formula for electrical energy is what? IVT or I square RT, which is the same thing as what? V square T over R. And since the electrical energy is being transformed to heat energy, let's say for instance you plug your boiling ring and you plug it inside the water, you pour water and you inside a jug and you put your boiling ring and you switch on your current, you switch on your what's it called, your socket. Now what you're actually doing is you are changing the electric energy, which is equivalent to what? The voltage multiplied by the current times the amount of time you'll be using the boiling ring. You have transferred that energy to the water, which means that the heat of the water will now be what? The mass of the water multiplied by the specific heat capacity and change in temperature of that water. That is what we have here. The next one is potential energy to heat energy. This one is very useful whenever we have a waterfall. Water is falling from a certain height. Calculate the temperature change. It's very simple. What is the energy that the water will possess at a certain height? Potential energy, which is what? mgh. Now it's giving us what? The same thing, mc change theta. Don't forget that all this energy can as well be equivalent to what? mlf, which means if you are using this energy and we are converting it to what? Latent heat of fusion. Let's say you are boiling, you want to evaporate some liquid that is already boiling, and you switch on your socket. You have a boiling ring and we use it to evaporate that liquid. What you actually do, what you have done there is you have converted the electrical energy towards the latent heat of vaporization. So it doesn't mean that you can have MC change theta here. You can also as well use this formula for MLF or MLV. Now the same thing with kinetic energy to heat energy. Let's say someone is actually running, you are given the mass, the speed, and let's say you have a mass, a body moving in air, and you are asked to calculate the temperature change. Is very simple. Most often I don't used to see this kind of, I don't used to see some question on that is, but I know you can use this formula to solve some question as well. Kinetic energy to heat energy. Next one is strain energy. This one I used to see some question here. Let's say you have a stone and you put it inside a string catapult and you shoot it. It's very simple. What you actually done here is you have changed the strain energy of your string and it has been transformed to heat energy on that stone, which means 1 over 2 kx square or 1 over 2 ke square, which is still the same thing as 1 over 2 fe is equals to what? MC change in theta. So I've divided some terms here. The first one is the mass, which is, the next one is your specific heat capacity, MC thermal heat capacity, LF I've explained it, K, which is also what? Force constant or stiffness of the material, E, which is your extension, G, acceleration due to gravity. You're all familiar with this. Now, method to determine your specific heat capacity. So we have different methods. The first one is electrical method. It's very simple. I've explained it. Just you have your boiling ring. Let's say you want to know the specific heat capacity of a block. Very simple. You weigh the block and you make some hole inside that block. Or let's say you have an ice and you dip in your heater here. You have this device and it is well lagged. Now, lagging is used to prevent heat loss or gain by your device, by your calorimeter. So you have your lagging here, you have your heater in the block or a liquid, then you have your thermometer here. Then you connect. Now, this heater is going to have a power rating. You can have the power or you can have the current rating and the voltage you are supplying to this heater, or you just have the power rating because it has and the likes on some device. Now it's very simple. You plug it to the source, electric source, and then you time it. The duration of the time that you have used multiplied by the power rating will be your what? Electrical energy. And don't forget to have measured the mass of this. It is going to be equivalent to what? To this mass multiplied by what? The specific heat capacity. Don't forget you want to know the specific heat capacity. Don't know it this time around. So, but you know the mass, and you have measured the initial temperature and final temperature. Just make your CS set of formula. Don't forget we know the time, we know the power rating, so you can equate your parameters to get your C. The next one, let's look at a simple example. The first question: all the heat generated in a 5 amp resistor by 2 amp flowing for 30 seconds is used to evaporate 5 grams of liquid at its boiling point. Calculate the value of the specific latent heat of the liquid. You can pause it and try. It's very simple, which means that we are using electrical energy is being transformed to heat energy. And what type of heat energy here? You have latent heat. Now, don't forget latent heat. And what type of latent heat do we have here? We have latent heat of vaporization. So which means electrical energy is equal to what? mLV. So let's look at the solution. So it's very simple. You are given the resistance of that heater, the amp, and the time, and you know the mass of your substance. The reason why I didn't convert this mass to kilogram is because the option in the past question, in that question, is in joule per gram. So the first thing, whenever you are given a question, before you start converting anything from one form to the other, just look at your answer. Look at the unit of your answer. That is why I didn't convert this 5 gram to kilogram. So yeah, very simple. You are given the current, resistance, and the time. What is electrical energy using that formula? I square out T, which is because what? mLV. Make your LV sort of formula by dividing both sides by m, so you get this. Substitute your value. So you have what? 2 square times 5 times 30. What is 2 square? 4. 5, we cancel 5. That is why we have 4 times 30. What is 4 times 30? 120 joules per gram. Now, the next method is you can use mixture method. This is one of the methods I discovered that many students don't understand. It's very simple. Now, for mixture method, heat gain is equals to heat loss. Heat gain is equals to what? Heat loss. Now, for bomb calorimeter, thank God I've shown you bomb calorimeter. It's very simple. Now, you have a melter block of known mass. So you are going to heat the melter inside the boiling water. Now, don't forget that the boiling water is having a what? If water is boiling, is at a certain temperature, 100 degrees Celsius, constant temperature, isn't it? Now, you have your melter block inside that water. You are boiling it. After a while, the temperature of this melter will also be what? 100 degrees Celsius. That is coming from zeroth law of thermodynamics, which says that if we have different objects at different temperature and you are bringing them together, after a while, they will have a what? A uniform temperature. They assume one temperature. That is what? Equilibrium temperature. So that is that about zero law of thermodynamics. So you know the initial temperature of this mass, which means that 100 degrees Celsius will be